Do you have a yellow green? Would that be green apple, or key lime, spring moss, or fresh cut grass wasabi, or lime sorbet? Alright, on page 16 we've looked at the refracting telescope that Galileo perfected, the reflecting telescope that Newton has perfected. Now we're going to look at this particular tool of the astronomy trade, and that is a spectroscope. So it's made up of lenses, quite typical for scopes. But what makes a spectroscope different is in the bend here, and that is a prism. It's a three-sided, usually acrylic or glass. And the reason for that prism, if you think of the Dark Side of the Moon album cover, it's passing the white light, so that's being received, and diffracting and refracting, spreading the light out and causing the light to refract into the various wavelengths of color. The world's largest spectroscope is in Annapolis, Maryland at the United States Naval Academy. The world's cheapest spectroscopes we used to make in class, you just got a cereal box, and CDs used to be quite prevalent. You had stacks of CDs that you'd get in the mail, you just didn't know what to do with, but now these are becoming the rarity. This is your kind of classic spectroscope, very close to the original model. And this one's going to bring back the memories for you. Chemistry. Chemistry is not a prerequisite or requirement for astronomy, but some of you have taken chemistry. These are the wonderful devices you waved around thinking you were seeing what you're supposed to be seeing, but probably weren't. You were hoping to see spectra off to the side of the spectroscope here, so seeing the different color frequencies, red being the lowest energy, the blues the higher energy. The measurements that are in the spectroscopes, these grades right here, those are in a wavelength measurement called the angstrom, of course named after Angstrom, a Swedish scientist. Google Doodle in his honor of the 200th time his DNA went around the sun. Sometimes I'll show you pictures where it's black with the bright lines being visible. Sometimes it's kind of the reverse, where you'll see the spectrum and lines as though they are missing. This, whether you see emission or absorption, this has to do with energy as your electrons transfer from one level to another. Or essentially, if light is traveling from or through a hot gas to Earth, we're going to see the emission spectrum. If light is passing through a cold gas, then we get this absorption spectrum. Here's another graphic to demonstrate that. Going from a cold source will get you the dark. Going through a warmer will go through the continuous spectrum. Now in the classroom, we'd have you don these diffraction glasses. So they have some plastic that have those etched with laser lines in them. And we'd have you look at light sources, and you would see these color spectrum thanks to the diffraction glasses, which are also known and sold as fireworks glasses, as it's quite fun to view the fireworks through these diffraction glasses. Looking at the stellar fingerprint, looking at the spectra of stars, gives us an enormous amount of information and is called spectroscopy. Looking at the spectral lines from stars, spectroscopy. One of the things spectroscopy allows us to do is to see what elements are in stars, or what the stars are made up of. Because the signature for hydrogen is always exactly the same. If you're looking at a pure source of hydrogen, you will always see this faint lavender line at 410 nanometers, this light blue 434 nanometer line, this green 486 nanometer line, and this red 656 nanometer. Remember, a nanometer is a billionth of a meter. And it's just a classic signature. So if we had, and this is what we do in the classroom, is we'd pass electricity through this hydrogen so that it got energy, emitted this light, and you would look through those diffraction glasses and you would see this unique pattern. So the hydrogen pattern. And these physicists, one is the professor, one is the student, they, at their graduation ceremony, had rather unique stoles. You see the red, the green. They had turned their stoles into the recognizable hydrogen. Here's the unique fingerprint of helium, where we'd put that gas tube in an electric power source, pass some energy through there for it to radiate, and you would see through your spectroscopes this great pattern here. Now, since we're not able to do that for you as we're not in the classroom, here's a video clip of how this would look. So showing you pointing the light source for the spectroscope. And then right off to the side here is the helium fingerprint. Carbon's unique fingerprint. Don't panic, I'm not showing you the whole periodic table of the elements, but this is one of my favorite representations of the periodic table of the elements, where this is actually an interactive website where you can click on the element and it will pull up the unique fingerprint. And if you just type in emission spectra of the elements periodic table, it'll take you to the Oregon website where this is housed. So if I look at a regular incandescent bulb through a spectroscope, you're going to see very broad red, green, and blue, the primary colors of light. When I look at more fluorescent type lighting, I can see the gases that make up the fluorescent properties of that light. When talking about reducing light pollution, we mentioned the high pressure sodium lamps and the sodium signature. Probably one of the more easily recognizable ones, because you either have this very apparent dark line or you have this very bright yellow sticking out, screaming at you saying, "I'm sodium." A monitor, spectral image, and an LCD display of a computer laptop. That spectra, different than the CRT monitor. A monochromatic light, so mono, single color, chromatic color. So a single color, the spectra naturally is only going to show you that color, that energy. So a candle flame, you see the very prominent red, green, and blue. And then on the end of a toothpick, we've put something on there. Actually, it looks like an open paper clip. We got a little element on there. And that element is screaming at you, letting you know that it is a form of sodium. It's not sodium alone. It's table salt, which is sodium chloride. But you can see the sodium component brightly screaming at you. So spectral analysis, looking at analyzing what we get from these unique fingerprints, is what we're going to look at here next with page 24. I've said it a few times now. What is the nickname for star spectra? We call them fingerprints because they're unique. Each star, each galaxy emits their own unique spectral lines. Why do we do spectral analysis? What we can learn from that? Well, there are many things that you can learn through spectral analysis. We're just going to have you jot down the top 3 in terms of top 3 that we'll use for this class. So in addition to stellar composition, star temperature, some relative motion of stars, you can also determine the mass, the density, the pressure, all kinds of properties from looking at the spectral lines. Looking at this latter one of motion of the stars, are they moving towards us or away from us, actually goes back to round off the Little Light Astronomy page. The gentleman on the page here is Christian Doppler. We'll give you clues to what country he's from. Maybe you don't watch the Winter Olympics and skiing, where Austria tends to dominate. Capital of Austria being Vienna. So the Doppler effect you're very familiar with when it comes to sound, but Doppler and his research team actually applied the Doppler effect to light first. But since you're more familiar with it with sound, let's refresh you of what the Doppler effect is.
So funny.
We'll play that again. So as the vehicle approaches, it makes a higher pitched sound because as it's approaching you, these wavelengths are decreased. So the frequency goes up and your brain registers higher frequencies as higher pitches. Likewise, when the vehicle moves away from you, those wavelengths are no longer contracted, so the wavelength is longer, making the pitch lower for you to hear. Again, this is the Doppler effect. The Doppler effect for electromagnetic radiation, so light, infrared, gamma radiation, X-rays, microwaves, and such. It's not that you're going to hear a higher pitch as something moves towards you, or a lower pitch as something moves away from you, as it does with mechanical radiation or sound. The EM radiation, you're going to have shifts. And these shifts are where the spectral lines, all in unison, so the same gap between the fingerprint, will all move more towards the blues or more towards the red side of the spectral analysis. It's not that, let's say, the source, called a star, it's not that the star is moving towards you and it's turning blue, or it's moving away from you and turning red. It's a matter of we're getting higher frequencies, and so we call it shifting to the blue. As we get lower frequencies, we see the spectral line shift to the red side. It's not as though I'm walking towards you and I suddenly turn into a Smurf when I'm blue. One of the ways I try and help you remember that blue means something is coming towards you, and red is moving away from you. Of course, you can jot this down in your notes, and you definitely want to clarify, because you have black and white notebook, you want to clarify that the top line, higher frequencies, are the blue, and the longer wavelength, lower frequencies are red. What it means, though, is a blue shift means that something is moving towards you, whereas a red shift is something moving away from you. One of the ways I try and remember this is I think of a character you might be familiar with called Superman. As he's flying towards you, you see more of the blue of his costume. When he's flying away from you, you see the big red cape. So when it comes to light, we're not actually saying that something turns red as it moves away from you, or turns blue as it comes towards you. It's an actual shift. So if I were to get this fingerprint of a star, and then say 6 months, 6 years later, 10 days later, well, that's probably too soon, 10 days, but after a substantial amount of time, I take a look at that star again, and I get this image, you'll see that I have the same spectral lines, so it's the same fingerprint, I have the same exact width in between the spectral lines, so it is that fingerprint, but now the fingerprint is shifted more toward this red side. So we're not saying the star is turning red, it's that the spectral lines are now more on the red side of the spectral fingerprint. That you would look compared to your baseline data and say, ah, that star is moving away from us. And this is what a blue shift looks like. It's the exact same fingerprint, same spacing, same thickness and thinness, but now as compared to this one, this is more towards the blue side of the spectrum. So we'd say blue shifted, and the star, the galaxy, is moving towards us. So another example with hydrogen, It's your baseline measurement. If you were to observe later, you'll see it's shifted now more to the red side, so it's a red shift, and this one is shifted more to the blue side, so it's a blue shift. Now this one, we had red on the right, and this one we have red on the left. That's okay. It doesn't matter. What matters is saying, oh, this line is now more in the red. Or with this one, this line is now more on the blue side of things. So in your notebook here on this page, if you were to see this, this is the blue side. We've shifted in this direction, so that would be a blue shift and the object is moving towards Earth. Or here, labeled the red side, it is shifted to the red, so we know that celestial body is moving away from Earth. Now, if we didn't have labeled blue and red, you wouldn't know if this was red or blue shifted, particularly on this black and white image. So I will always label for you blue and red sides so you can more readily detect, is it a red shift or a blue shift? Remember, this is also the helpful strategy I've incorporated into your notebooks, that when you pick up your notebooks and hold them with your name side towards you, the cover is blue. It's towards you. And the back cover of your notebooks I purposely make red. You tend to hold that away from you. So red, something's moving away from you. This is the Doppler piece of the moon. And this is food for thought. This shirt is blue if you run fast enough.